Welcome to example number 4 on rotational kinematics. In the graph that's shown below, we see the angle that is plotted versus the time for some object that's moving in a circle with a radius r. We're asked to describe in words the motion of the object and also draw the angular velocity versus time graph. So first of all, let's go to the graph just to understand that as well. To create the graph, we need to remember that the angular velocity is defined as the change in the angle, theta, divided by time, which if you look at this graph, since we're plotting theta on the y-axis and time on the x-axis, that's really just the slope of this theta versus time graph. So if we calculate the slope at the different segments, say it's from 0 to 3 seconds, and then 3 to 5 seconds, and 5 to 6 seconds, then we'll know what the angular frequency is over those time periods. So let's do that. So for 0 to 3 seconds, the angular frequency would be the change in theta over change in time. And so if you look at this, we have a rise of 6 pi, all over a run of 3 seconds. So we have 2 pi rads per second. If we look from 3 seconds to 5 seconds, we can find the angular velocity. Except this case, it's going to be dropping from 6 pi down to 4 pi. So that's a drop of 2 pi, all over a period of time of 5 minus 3 seconds, which is 2 seconds. So the slope in this case is pi rads per second. And then lastly, for the last second, 5 to 6 seconds, the angular velocity over time would be not changing. It's staying at 4 pi. So it's 0 divided by 1, which is just 0. So there's no angular frequency. So let's go ahead and now draw the graph for this. And there I plotted an axis of the angular frequency on the vertical axis and the time on the x-axis. And so we can see that during the first 3 seconds, there's a constant slope, and that slope is equal to 2 pi rads per second. So for 0 to 3 seconds, we have essentially a horizontal line. Then from 3 to 5 seconds in here, we have a constant negative slope of pi, negative pi. So from 3 to 5 seconds, we have another horizontal line below the x-axis. And then lastly, from the 5 to 6 seconds, there is no slope, so there's that line right in here. And you can leave the graph like this if you wish. Sometimes people like to put these dashed lines between here and here, and here and here. You wouldn't put a solid line in here because that wouldn't be a function anymore. Okay, in terms of answering the question where we describe the angular motion of the object, I don't have any space to write it down, so I'm just going to explain it in words. So I would break it down to 3 sections. For 0 to 3 seconds, the object is moving here at a constant angular velocity of 2 pi rads per second. And it does that continuously, so it's a nice horizontal line. So it's rotating, by the way, what direction? If it's a positive angular frequency, if you recall in our sign convention in our notes that we established earlier, positive angular frequencies and positive angles and positive angular accelerations, those are all counterclockwise direction. So in the counterclockwise direction. Then suddenly at 3 seconds, it's kind of hard to imagine because this is a picky point and wouldn't be really a true function. But anyway, suddenly, right at this point right here, it just switches from going to a positive angular velocity to then a negative angular velocity. So this is now a constant negative angular velocity, but it's about half, it's exactly half of what it was before. So negative pi rads per second. So it's going in the clockwise direction during this section right in here. So from 3 to 5 seconds, it moves in the clockwise direction at a constant angular velocity, about half the rate that it was going at before. And lastly, for the last second, it just basically it stops. Suddenly stops at 5 seconds, and it's at rest for the last second. And that's it for this example number 4.